This is the fourth electromagnetism video for A-level physics. The aim of this video is to consider the size of the induced voltage, the rate of change of magnetic flux, and Faraday's law. These are all really just one idea. In the previous three videos, we have studied flux and the effect of changing flux through a loop. Additionally, voltage induced is directly proportional to the rate of change of flux. Well, whenever we're talking about a rate of change, we're talking about something, some change in something. That something here is the flux. The rate of change, so the change of something, flux. So delta phi, change in flux. Over the time it takes, right? Over the time refers to rate. There is one law in physics that brings these ideas together, and that's Faraday's law. It will take a bit of time to build up to that. Okay. So we need to consider a coil. A coil is made up of many loops, or people will say turns of wire. So we're going to need to draw one of these that we can refer back to as we go. Okay, here we have our loop. We can see that this is a loop if we just follow this and sort of work our way around in the way that a current would work its way around this. That's the first loop. Green's the second. And we've completed the third. We'll just go through and get the fourth. Right, that's a coil made up of several loops. Here we've got the first loop drawn in red and the second loop drawn in green. We need to keep in mind what happens to just a single loop, because a coil is made up of multiple loops. So if we know what happens to a loop, we can then extend that to a coil. So the key idea is this: if the flux through a loop changes, then a voltage is induced across that loop. Earlier it was stated that the voltage is directly proportional to the rate of change of flux, but we can actually go further and we can say that the voltage induced is equal to the rate of change of flux through the loop. So we'll write that down. Voltage for a loop is equal to the rate of change of flux through that loop. I'll take that idea on. We should consider another picture, because we want to get the idea across that the flux going through one loop will be the same as the flux going through the other loops. That is, if the field is uniform and directed perpendicular to the loops. So we'll bring in another picture for that. This picture just focuses on the first two loops, loop 1 and loop 2, and it treats them as if they're completely separate loops. They're not part of one coil, but that will make it easier to see what's going on. We can see if we look very closely at this picture, it's easiest just to look at the dots that are sitting on each surface, like that. We've got these 9 dots, and they're the points where a field line passes through that red loop. Well, we see that those same field lines all pass through this loop as well. So if these loops are aligned like this with each other, just like they would be in the coil that we're looking at right here, the flux through one of them will be the same as the flux through the other. We'll get that idea down. So the flux through each loop is the same. And then we can take that even further. So if they've got to be the same, they all have to have their flux change at the same rate. If one of them loses a field line or some amount of flux in 1 second, then all of them, each loop, lost that field line. So they have the same rate of change of flux. Each loop has the same rate of change of flux, phi. And we've also established that if something has a rate of change of flux, that means that that's not zero, so the flux is changing, then there must be some voltage induced. So we can say that V here is the voltage induced across each loop. Now, if we look at the main picture again and go back through the way we did before, this coil is not only constructed of a set of loops, but a set of loops that are arranged in series, right? They come along one after the other. The red one is then attached to the green one, and then the third one is attached to the fourth, which is attached to the fifth, and so on. They are connected in series with each other. The loops of a coil are connected in series with each other. And we know from electricity that when voltage supplies are connected in series with each other, the voltages add up to make the total voltage. So we can say the total voltage is the sum of all of the loop voltages. And let's say that there are we'll just say there are n loops in one of these coils. N loops in a coil. So we have to add up V plus V plus V plus and so on until we've done this n times. A more sensible way to write that would just be to say, oh, we've got n V's, n times V. That's the voltage of the coil, right, the total voltage. If we go back though and look at this point, V is equal to the rate of change of flux, delta phi over delta t. So we can write this, V coil is N delta phi over delta t. That is a very important equation. That's essentially the equation that expresses Faraday's law. Again, we will get there very shortly. A new quantity has crept into our work here. If we rearrange that equation above, we can write delta of n phi, like the change of n times phi, over delta t, the time elapsed, the time that has to pass in order for the flux to change. This quantity n phi is called flux linkage. It's just the number of turns in the coil multiplied by the flux through each loop in the coil. At this point, we can now come out with Faraday's law. So let's write that out. Faraday's law. Faraday's law states the induced EMF, really we just mean voltage there, the induced EMF is directly proportional to the rate of change of magnetic flux linkage, that new concept, flux linkage, which is n phi, the one that we saw up there. Let's write this proportionality out. So EMF is directly proportional to the rate of change, so change of flux linkage, n phi, over the time it takes to change. In practice, it is much more useful to write this instead, though. EMF is equal to the rate of change of n phi over, the rate of change of flux linkage. Because with the proportionality, we can't really work anything out, whereas with this proper equation, we can work something out. It's worth noting that this doesn't tell us anything about the direction of the induced voltage. It just tells us the size, whether we'll get 10 volts, 50 volts, 100 volts, but it doesn't tell us which way a current would flow if that voltage was created in a complete circuit. It just tells us the size of the induced EMF. Okay, in the next video we'll look at a few calculations that require use of Faraday's law, and in particular this equation we've got in a box here. Okay.